Okay, I don't know how much of the lecture it missed, but hopefully not too much. Yeah, it's Z, right? It's the same side, right? This methyl group is on the same side. That's not that, right? That's epicet. So what does that tell you about the transition state of a Cope rearrangement? Is this transition state that we'd like to go through? No, right? And in fact, you could probably predict that already, right? They could ask somebody that's gone through chair confirmations, they could tell me, I don't like that. I don't want that group to be up there, right? So what do? You do a flip, right? Okay, so I'm going to do a chair flip. Okay, so now, oops, I screwed up. So remember when you're doing these ring systems sometimes, and I just screwed up my first time through as well, so I caught myself, but it's a good idea to sort of number your carbons so you don't make these mistakes, right? But if I have 1, 2, 3, 4, that's going down, I want it going up, which means this is going to be 3, 2, 1. Right, so if this is 4, right, because it's going down, it's going to be going up. I want the up to now be equatorial. Right? Do you guys see that? I kind of drew it small. Let me try to draw it a little bit bigger over here so you guys can see. Right, so I just drew it bigger so you guys can see. Right, so that molecule there is that one there. Can you guys see that in the back? Okay. All right, so when this goes through, cool. Now my methyl's staying up, but because of the way that the chair is drawn, what's the stereochemistry of my alkene now? It's trans, right? And in some ways this makes sense. If we consider like our chair conformations, right, in general, again, those of you that sort of had my class, we sort of talked about how, right, as we're sort of looking over the chair, we sort of merged chair conformations with Newman's to a certain extent, right? And we sort of saw how certain bonds are axial to one another, right? And when we consider an alkene, right, they're anti to one another, excuse me, right? And when we consider an alkene, right, it's pretty standard to see on an alkene which groups are kind of anti to one another on the alkene, right? It's the trans molecules, right? And if you sort of consider if you have an equatorial group there, right, and you're looking down, for example, that bond right there, call that A, we'll call this E and A for, so I'm looking down that bond there, here's the ring, two protons there. Right? So if we're looking at the sort of this bond here, right? The relationship between this bond right there is the bond in the back. So this bond here and this bond here are axial to one another, right? The analogy there, these two bonds being axial to one another, is the analogy here, right? That those two bonds are axial to one another, right? Conversely, sorry, I said axial, misspoke. Anti, let me just restate this. Let me just say it again, just so it's clear. This group here, the equatorial group, and this bond are this bond and that bond. They are anti to one another. Right? They are anti to one another. Because they're anti to one another, right, the analogy would be this bond and that bond, right, which ultimately become this bond and this bond. When bonds are anti to one another, right, it sort of makes sense that in an alkene, you could also have the anti one another, right? Compare that to I sort of drew it upside down, but compare it to the axial, right? The relationship between the axial and this one, they're sort of gauche to one another. They're close to one another, right? And so when that elimination takes place, it's going to skew and they're going to become same face. So do you guys see this? Gore? Okay. So we'll do a few more examples on a few more challenging problems, but you can clearly see one of the things that I like to emphasize on the chair on the Cope and Claisen is I like to ask questions that require that you can draw sort of chair-like transition states. Okay. Okay, so this is one that's. Can I erase this? Okay. Okay, so that's a fairly straightforward one. But let me give you guys maybe a harder question. Which is one maybe with two methyl groups. Okay? And those two methyl groups right? And so if I do a Cope rearrangement with one, right? So there's basically two possible stereoisomers of my initial Cope. Right? One of them is going to lead to trans-trans, right? That's a safe bet. We're not going to get the cis-cis, right? Because the cis-cis would be two axials at the transition state, right? But one of them, right, will likely lead to trans, and one of them will likely lead to one trans and one cis. Okay? So what I want you guys to do, before I go over this, I want you to maybe spend a minute. Try to draw, let's maybe just start with this one for starters. Try to draw this one, just like I did before. All that you need to do at this point is add an additional methyl group on there. So try to draw this one here, and ask the question, does that lead to both trans, or does it lead to trans and cis? And I'll give you guys a minute to think about that. Remember, if you're struggling to draw, what you may want to try to do for starters is if you have a pencil, try to draw the chair just straight up. Right? Just draw the chair, and then what you can do is you can erase one of the bonds and fill in the rest, okay? And in fact, after you draw the chair, and then you go to the product, then you take it to the product, right? What's going to happen? The group that's axial, if there's a group that's axial, well, certainly if there's a group that's equatorial, there's bound to be at least one group that's going to be equatorial. The question kind of is, you know, when one is equatorial, is the other axial? Or when one is equatorial, is the other... One's equatorial, is the other axial? Or is the other one equatorial, right? Is it equatorial or equatorial axial? Does that make sense? Because the axial, if you draw it and you end up with the axial, what do you got to do? Draw the chair flip version, right? You want to, if it's axial, if you draw it and it ends up being axial, then you want to go to the okay. How you guys doing? Anybody have anything? Okay, Brianna, what do you think?
I think that is cis.
So Brianna thinks it's going to be cis-trans. Anybody else want to agree or disagree with Brianna? That's a no. Okay, I'll give you guys another 10 seconds or so. What's that? So once you draw it in the chair, you're going to have some options, right? It's either going to be, the two methyl groups are either both going to be equatorial, they're both going to be axial, If they're both axial, you probably want to do a chair flip, right? Because they'd rather both be equatorial, if that's what you get.
We're just talking about that one, right?
I'm just talking about this one right now.
Yeah.
Right? So are these methyl groups, when we draw them, are they both going to be axial?
No.
Are they both going to be equatorial?
No.
One's going to be axial, one's going to be equatorial.
Yes.
Okay. If one is axial and one is equatorial, which one do you think it's going to be? Yeah. Right? Because the equatorial, which is lower in energy, right, is going to lead to the lower energy alkene, right?
It's
Because
okay, we drew it the opposite, like upside down.
yeah, so just to sort of complete this so that we can sort of see it, right? Good. Right, so that's going to be methyl equatorial. So that's going to be that one. Oops, I'm on the wrong side. Sorry. Right, so this methyl group will be here. It's going up. It's going to be methyl. Right? Down it's going to be proton. And then this is going to be the other methyl group. So this is equatorial, as I've drawn here, because it's going up. This is also going up. So that's going to be axial, right? And so when we do co-rearrangement, right, this bond here right? 1, 2, 3, 4, 5, 6, right? So this bond here, the double bond that's forming, hold on, sorry, I completely screwed that up. Right? This bond here is kind of that one there, right? It's going to be trans. See that? It helps to put in the proton because the proton's going down, right? So that alkene there, that bond right there, that double bond, is the one that emanates from that, right? The methyl group, make this a little bit smaller so they're not running into each other, right? That's the trans. And then this one over here, right, that becomes that bond there, which is that one, right? And that's cis, okay? So this would be this one, okay? So this goes to this, which means, right, that this one would lead to that one. Okay, and so if we drew the same thing, right, we see in that case that now both methyl groups, this is going up, so it's equatorial, that's going down, so it's equatorial. Both those will subsequently become that one there. You guys see that? Yeah.
Can you just explain one more time?
Yeah, sure.
How you did the last thing?
This one here? Okay, so all I've done is I've drawn this 6-membered ring, right, as a chair, right? Now, I put in the substituents to sort of mimic this sort of pseudo-chair-like transition state, right? And what happens is, when these bonds form, if I go, maybe I help to go 1, 2, 3, 4, 5, 6. Okay, the one carbon, right, is this one here. That's 1, right? 2, right? Because we're making a double bond. When that shifts over there, we're making a bond between 1 and 2. That's becoming that. 1 has a methyl group on it. It's breaking, right? That sort of 1,6 bond is breaking and becoming a double bond between the 5 and 6. Just complete that. Right, so the 1 breaks, so that's why we don't have a bond there anymore, right? This methyl group's this methyl group is equatorial. When you have an equatorial substituents, right? It's as we sort of were saying based upon that chair, it's kind of anti to the ring, right? So basically, it doesn't have that 1,3 diaxial interaction. It's sort of out. So it's kind of going the opposite direction of the ring. So when it forms, right? You end up getting a trans double bond, right? Another way to sort of rationalize that is equatorial is lower in energy, trans double bonds are lower in energy. So the lower in energy sort of makes sense, right? The lower in energy substituent would lead to the lower in energy, right? Alkene, right? So that's that one, right? This one's axial though, right? So an axial substituent on that pseudo chair will lead to, since it's higher energy, it leads to the higher energy cis alkene. Or otherwise, we could think about it as we sort of show here, is that the axial is next to the ring when it does that elimination. Does that make sense? Okay. And again, we don't have too much time. I just want to talk about, only got about 7 minutes left. I do need to talk about I want to talk about Cope elimination, or Claisen rearrangement really quickly. But these could be a little bit more complex, right? I could say, for example, have a molecule like this and throw a substitution here or maybe here, right? What impact would that have on that, right? So we may, maybe we'll talk about a few of these more complex examples maybe on Monday, but should be problems. Leave on my website, but you could try to figure them out. You could try to go through them on your own, right? Put some different substituents there. Notice, for example, that in this case, right, we just have two methyls, so they're same sterically. I mean, what would you think would happen if one of those groups was, say, for example, a terbutyl? Yeah.
Then that would have to be the equatorial.
Yeah. So if you had a big bulky group, so if the groups are different, right? If one of the methyls was a T-butyl, right, then the T-butyl is bulkier. That's going to want to be equatorial and subsequently become trans, right? And so a lot of the things that we learned from within chair conformations will also come through on this. But I want you guys to be able to draw these chair-like transition states and use that to sort of reason the stereochemical outcome that you're going to get. And again, much like the Diels-Alder reaction, I truly recognize that this is a bit of a challenge. And it's going to take some time to practice and work with, but really fight through it. And once I think you come through and you click and see it, it won't be that hard, right? It's going to be difficult up front, but if you put the time in to get comfortable with it, it won't be that hard. And it'll be a lot, in the long run, build the skill of seeing in 3 dimensions, which is valuable for all of organic chemistry. And it also will mean that you won't have to memorize rules and different things. You can just draw it, and you can look and rationalize it that way. And so that's the skill that I recognize is within drawing. We've been building in terms of our ability to draw structures, right? And this is kind of the pinnacle of that for undergraduate organic chemistry, drawing chair transition states for the Cope and Claisen. So the only thing that differs. The difference between the Cope and the Claisen is simply oxygen. Okay. Claisen. This is Claisen rearrangement. And we've seen Cope eliminations. Have we seen Cope elimination? We're going to see Cope elimination. So this is a little confusing. So it's important to recognize that we've seen Claisen condensation, right? So let's not get too confused with these names. There's Claisen condensation, there's Claisen rearrangement, there's Cope rearrangement, there's also Cope elimination that we're going to learn in the amine chapter, okay? The Claisen rearrangement is simply if you stick an oxygen in there, okay? And notice that I haven't shown the reversibility arrow. This can be reversible in certain specific examples, but in general, most of the time you're going to find that the Claisen rearrangement is going to go in the direction that I showed, unlike the Cope rearrangement where you have to consider what the substituents are in those. Right? Actually, let me revisit that really quickly. So when I put the methyl groups here, and it led to there, that's a reversible process. Which direction do you think that reaction is going to favor? Yeah.
That one, because it's a more substituted the
Yeah.
double bond.
Exactly. So I meant to say that. I don't know that I actually ever said it. That's why I meant to get to that punchline. Does that make sense? Right? The cope is reversible, but this one has a more substituted double bond, so it's likely going to favor that direction. Right? Does that make sense? Here's a Claisen. This generally goes in this direction. Why might that favor that direction? What have we seen quite a bit? Yeah.
The C double bond O is more stable than a C
Yeah.
double bond C.
So we've seen a lot, right? This has been a theme, especially during the carbonyl chapter, right? This has been a theme, right? Where carbonyls are stable, are more stable, right? We saw this with the enol keto tautomers, right? This is an enol. It's kind of like enol keto tautomerization in some ways, except it's not a tautomerization. So, but it's you're going from an enol ether, right, to an aldehyde, and so this will generally favor the direction that I've shown. Okay. Same thing will hold true sometimes with substitution here, but it also raises up some possibilities of, we can imagine putting different groups in these positions and going through the same exercise that we did before. I don't think we're gonna have time to go through that. So we've only got 2 minutes. Let me just finish with a question, a concept question for you guys to sort of think about. I think this would be a good maybe question for an exam, maybe. And that's, can anybody maybe guess or think of ways that we could force this to go in the reverse? And maybe I'll just leave you with that thought. So let's okay, or Abraham, go ahead.
Yeah, heat makes everything go first.
What's going to make the global equilibrium favor this way? Heat will certainly increase the reversibility, but if it's already a thermodynamically driven process, in general, if this was 99% this, 1% this, for example, I just made up those numbers, I have no idea, but let's pretend that this is 99% this, how might we try to flip that script? How might we make this one, say for example, 99%? Yeah.
Well, wouldn't it be like a similar idea with the enolate, like the ketone and enol, and how to reverse it from a ketone to an enol?
Well, how would we do that?
We'd add an LDA, or just in general, I'd put it into conditions where the enol is more reactive than ketone.
That's an enolate.
Oh.
This is an enol, right? You can't really get a negative charge on that oxygen. I'll just leave you with that thought. I mean, class is basically over. So let's see if you guys can come up with stuff by Monday. Don't go nuts thinking about this, but just let it sit in the back of your head and think about how you might drive this in the reverse direction.